Thank you for introducing me, and I'd like to thank the organizer for being invited to Pohang University and giving me an opportunity to talk here. So to make my result clearly, let me give a subtitle, which is obstructive divisor to Kähler-Einstein matrix. As my subtitle, I'm talking about a problem in differential geometry, or more precisely in Kähler geometry. So first part, I will talk about differential geometry, and the second part, I will talk about more algebraic geometry. Today I'd like to discuss about existence problem of Kähler-Einstein matrix on Fano manifold. So I'm consider n-dimensional compact Kähler manifold with Kähler class large omega, and I consider Kähler metric omega like that. Then Kähler metric is Kähler-Einstein, means each curvature form is proportional to Kähler form. So this equation can be reduced to a partial differential equation of potential function like this, which is called Moduli equation. So this problem is purely analysis. But nowadays this problem is related to algebraic geometry. So let me quick review known result and conjecture, the famous conjecture. As you might know, we have always Kähler-Einstein matrix if the first rank class of the manifold is non-positive, which is proved by Orban and Yao. But Fano case, the problem is still open. But the uniqueness problem is solved by Bando and Mabuchi. So the problem is still open, means the Fano manifold not always have Kähler-Einstein matrix. So we have several obstructions, which is, for example, Matsushima's obstruction or vanishing of Futaki invariant or some stability condition. On the other hand, we have at least two sufficient conditions for existence of Kähler-Einstein matrix. So one of them is alpha invariant introduced by Tian. Maybe today or tomorrow it will be discussed. The second one is a multiplier ideal sheaf, which is one of my interests in this talk. And a famous conjecture which is proposed by Yao and Tian and Donaldson, so which says the existence of Kähler metric of constant scalar curvature on polarized manifold. XL is a polarized manifold X with polarized amplitude band L. So we can consider a pair of XL is algebraic variety. So this conjecture says if such polarized manifold has constant scalar curvature Kähler matrix, if and only if the manifold is stable in some sense from geometric invariance theory. From easy calculation, we found Kähler-Einstein matrix is a CSCK matrix. So this conjecture can be applied to Kähler-Einstein problems. And at this moment, this conjecture is still open, and still I don't make the definition of stability of manifold clear. So because the problem is we don't understand aware yet about what is the stability of manifolds. But we have several candidates, and we already know if we have a special metric, then it implies stability, some stability. So, for example, the following is a known notion of stability of manifold. So, the first one is K stability, which is introduced by Tian, and after that, this definition is reformulated and simplified by Donaldson. And this K stability has been one of the best candidates for previous conjecture. And the second one is a more classical stability, which is called asymptotic Char or Hilbert stability. And the third one is slope stability induced by Julius Ross and Richard Thomas. So this slope stability is an analog of slope stability of vector bundles. So this third one comes from the Hitchin-Kobayashi correspondence for vector bundles. So the last one is introduced very recently, precisely last week, by Donaldson. So K bar stability and V stability. So this means that this is some kinds of generalization of the K stability. So this means that we don't understand what is a stability for which corresponded to existence of special Kähler metrics. So anyway, in this talk I'm talking about the first one, K stability. But my main result is a bit not directly related to this conjecture, but so anyway, let me explain my motivational question. So there are at least two conceptual grounds for Yao-Tian Donaldson conjecture. So why we believe the conjecture is true is one of the reasons is it is analogy of Hitchin-Kobayashi correspondence, which says if a vector bundle, a holomorphic Hermitian vector bundle has Einstein connection or Einstein matrix, if and only if the vector bundle is satisfies the slope stability. So this is already proved by many people. So the previous conjecture is an analogy of Hitchin-Kobayashi correspondence. So this slope stability is the original one. So this the Ross-Thomas slope stability of Ross and Thomas comes from this slope stability of vector bundles. And the second reason is comes from moment map. So by Fujiki and Donaldson, we can consider the scalar curvature is a moment map under the infinite dimensional Lie group. So formally we can take a symplectic reduction under this moment map. Then so we can believe we can have corresponding GIT quotient, but still we are not what is a GIT quotient for the manifold. So yes. So what I'd like to talk here, what is obstruction to the stability and the metrics. So in the vector bundle case, subsheaf obstructs the stability. So slope stability defines a slope for subsheaf. It means let E be a vector boundary. So E is slope stable. If and only if any subsheaf of E satisfies this inequality. So this quantity is called slope of f. So this definition says if vector boundary is not slope stable, then we have a destabilizing subsheaf which violates this inequality. So in the vector boundary case, the obstruction is a subsheaf. So in the manifold case, so I'd like to ask what is an obstruction. So for example, in the Matsushima's obstruction and the Futaki obstruction, obstruction is a bad Holometric vector field, so which violates the existence of K-Einstein matrix. And in the stability, obstruction is some bad deformation of a polarized manifold or its limit. So this means if a manifold is not stable, then we have a bad deformation and we have a bad limit of the Fano manifold. And the last one is in the Nadel's sufficient condition, the obstruction is some bad coherent ideal sheaf or its associated subscheme. So, but this violates K-Einstein matrix, but we don't know first one and last one obstruction stability. We don't know that. So anyway, I want to know what is the obstruction to both of matrix and the stability. MIS is multiplier ideal sheaf. So this K stability comes from the Hilbert-Manifold criterion in the geometric invariance theory. So this means we take, to define the K stability, we take a deformation of the manifold. So it is an algebraic deformation. But now we consider the differential geometrical deformation, which is each flow. So we have a two side. So in the algebraic side, we consider the stability. In the differential geometry side, we consider the matrix. And to define the stability, we need a algebraic deformation. So the corresponding things in the differential geometry, it is a Ricci flow. So as you see, Ricci flow is defined by this equation. So if this equation, the solution of this equation converges to at infinity, the solution will converge to K-Einstein matrix because this side will vanish. So this flow converges to K-Einstein matrix. but we already know the global existence of Kähler rich flow, but we don't know when it's converged at infinity, because it's directly related to the existence of the problem of Kähler-Einstein matrix. So if a Fano manifold does not admit Kähler-Einstein matrix, of course the solution does not converge in smooth sense, but it still converges in a weak sense. This means taking a sequence of Kähler rich flow and we normalize phi t by phi t I minus 2 phi t phi, then we have a limit in the weak sense. This means this is not smooth, so somewhere it has a singularity. It will be diverged to minus infinity, but phi infinity has a looks like a log function. So phi infinity has still satisfies some convexity like this one. So we can consider this is not smooth scalar manifold, because somewhere this form is not strictly positive. So, but we can consider this is a degenerate Kähler form. So we call phi infinity omega pre-subharmonic function. So then I'd like to ask, what kind of singularity does phi infinity have? So to describe the singularities of phi infinity, we can use a multiplier ideal sheaf. And relating to these topics, we have two known results. So first one is a famous one. In the viewpoint of complex analysis, the results like this one. So this is initially proved by Nedel, and after that it is simplified and generalized to orbifold case by Dumay and Cora. The recently, so but first two results is proved for Monge-Ampere quotient or continuity method, but recently those results is proved for rich flow by Rubinstein. Let me explain this. If let X be an n-dimensional Fano manifold which does not admit Kähler-Einstein, and we assume that X has a compact subgroup of holomorphic automorphism group of X, then we take G invariant initial Kähler form, and we flow at omega naught. Then, because X does not admit Kähler-Einstein, so we have phi infinity with singularity, some singularity. Then we consider the multiplier ideal sheaf of gamma phi infinity, which is GC invariant. GC means a complexification of Z. Z. Then a multiplier ideal sheaf satisfies this one. So it is not structure sheaf for any gamma in from n over n plus 1 until 1. So the definition of multiplier ideal sheaf is this one. So I gamma phi infinity has pre-sheaf defined by this one. So if phi infinity diverges to minus infinity, then this function is not integrable. So that ideal sheaf describes the singularity of phi infinity. And we know that is coherent. So we can define the associated subscheme cut out by multiplier ideal sheaf. We denote it by V gamma phi infinity. So anyway, what I want to say here, if a Fano manifold does not admit Kähler-Einstein matrix, we have some coherent ideal sheaf or its associated subscheme. it means if manifold does not admit such subschemes, then manifold will admit Kähler-Einstein matrix. So to apply this theory, we need to make this subscheme more restrictive. So what is this? For example, if a manifold has a very high symmetry, then we can show non-existence of such subschemes. Anyway, in this case, the obstruction to Kähler-Einstein matrix is a subscheme. So the second one is more algebraic geometry. So this is proved by Cora or explained by Cora, because this theorem is just the statement of the previous theorem. So the situation is the same as before. Then instead of subscheme, in this case we have a Z invariant effective Q divisor, such that D is numerically equivalent to anti-canonical divisor, and a pair of manifold and n plus epsilon over n plus 1 D is not Kawamata log terminal for any positive constant epsilon. So this is a more algebraic result. But the statement is, in some sense, these two statements are almost equivalent, because if manifold does not admit Kähler-Einstein, then we have a degenerate limit of the Ricci flow. So first result, this phi infinity induces a subscheme. Second one is a divisor. But anyway, these two come from the same phi infinity. So in this case, the obstruction to Kähler-Einstein matrix is just divisor. But second one has more application than previous one, because first one is a subscheme, the second one is a divisor. So divisor is easier to handle rather than subscheme. So actually, this theorem, by using this theorem, Cora proved the existence of Sasaki-Einstein matrix on some Sasakian manifold. So anyway, we have two obstructions for Kähler-Einstein matrix. In this case, I put on a definition of Kawamata log terminal similarity, and so a pair of manifold and divisor is KLT, means for any proper bimenomorphic map from Y to X, then we have a Q divisor dy such that this equality. So Kawamata log terminal means all coefficient small ei is strictly less than 1. So this definition equals equivalent to the algebraic multiplier idea sheaf of xd is trivial. So algebraic multiplier idea sheaf defined by this equality. So anyway, second statement is pure algebraic geometry statement. So my question is, what is the difference between the previous two facts? The first question is, is this subscheme also divisor or not? The second one, if the answer to first question is yes, then is there any relation between the first divisor and the second divisor, or is there any difference between them? And the final question is which divisor or which one violates stability? Because both of them violate the existence of metrics, so what I want to know is which violates stability. So I consider this question in the case of toric Fano manifold, because this is in the toric case we can work easily in both sides of algebraic geometry and the differential geometry. So my main result of this talk is the answer to first question is positive in some sense. So let X be an n-dimensional toric Fano manifold which does not admit K-Einstein metrics, and and we consider a compact subgroup of holomorphic automorphism group, or holomorphic automorphism group of X is generated by a torus action and a while group of torus in holomorphic automorphism group. Then we have phi infinity. So the statement says the support of multiplier ideal subscheme contains some torus invariant divisor set theoretically for any gamma in interval from 1 over 2 until 1. Anyway, this theorem says the answer to first question is positive in some sense. So this is the first part of my talk. So is there any question or not? So let me continue. So maybe I skipped proof because in some part of my proof works with differential geometry, so I skipped. So, but let me remark one thing. In the toric case, the behavior of Kähler-Ricci flow is quite simple because we have a Soliton solution for Ricci flow. So analytically, the proof is not difficult, and the problem can be reduced to a combinatorial problem. So to determine the support of the multiplier ideal sheaf, we can use some numerical quantity to determine the support of V gamma phi. So that quantity is called complex singularity exponent in complex analysis. In algebraic geometry, it is often called a log canonical set fold. So the definition is like this. So let psi be an pretty subharmonic function, and let P be a point of manifold, Fano manifold. Then we define the C P psi by sup of C such that exponent minus C psi is integrable around sorry, this is a mistake, around P. This means this quantity measures the singularity around P. Eventually, we found support of V gamma psi is equal to P satisfies the CP psi is strictly less than gamma. So anyway, to determine the support of the multiplier ideal subscheme, it's sufficient to calculate this quantity. And we have a combinatorial formula to calculate such quantity like this. So what I want to emphasize here, this inequality is equal or greater less than 1/2, because this number is integer and this number is negative. So anyway, if a supported multiplier ideal subscheme contains a torus invariant divisor, then the complex singularity exponent around the divisor is equal or less than 1/2. So this number appears in this number. So this is independent of the dimension of manifold. So anyway, we found the multiplier ideal subscheme comes from each flow has codimension 1 in some sense, because I don't consider pure dimension. So, but it seems to be difficult to calculate multiplier ideal subsheaf, multiplier ideal sheaf itself or subscheme itself, because the situation is quite analytic, so they might have more complicated structure. But we can, in the toric case, we can replace multiplier ideal subscheme by the simpler one. So let X be a toric Fano manifold which does not admit Kähler-Einstein, and G is the same as before. Then we have a multiplier ideal subscheme from each flow. But we know the multiplier ideal subscheme has a multiplier ideal subscheme contains a torus invariant divisor, and we can calculate the associated complex singularity exponent. So then we can define this divisor. So Di is a torus invariant prime divisor. The coefficient comes from the inverse of complex singularity exponent. So from my result, Di is greater or equal to 2, and the coefficient is integer. So, and d phi is torus invariant, and it has simple normal crossing support. So its associated multiplier ideal subscheme in the algebraic geometry sense is defined like this. This is cut down of the coefficient gamma di. So from this equality, we can find easily the support of multiplier ideal subscheme b gamma phi infinity is equal to the support of the b gamma d phi infinity. The right side is a algebraic multiplier ideal sheaf. Left side is a analytic multiplier ideal subscheme. So anyway, from this proposition, we can replace analytic multiplier ideal subscheme by algebraic multiplier ideal subscheme. So then, let's move to the second question. So what is the difference between d phi infinity and the Collat's divisor? So obviously, d phi infinity not necessarily numerically equivalent to anti-canonical divisor, and all coefficients are integers and greater or equal to 2. In particular, it is not KLT. So d phi infinity has the same similar similarity as Collat's divisor, but it's not same. It's not same as Collat's divisor. So then let's move to the final question, which is an obstruction to K stability. So from now on, I'm talking about more algebraic geometry. So let me explain the definition of K stability first. So here, I don't assume the manifold is Fano. For any polarized manifold, we deform the XL like this one. Simply, this deformation is a flat deformation. So calligraphic X is parameterized by C. Generic fiber is isomorphic to the original manifold, but central fiber is not necessarily isomorphic to original one. So generic fiber is a smooth one, but central fiber might have some similarity. So we assume that this is just scheme. Then we assume that C star action on calligraphic X. Then this C star action act on the central fiber, and we can define its weight of C star action. Then we can define some quantity which is called the Stucky invariant on the central fiber. So K stability is defined by these two things. One is a deformation, one is some kind of weight of the C star. So K stable means for any deformation, we have a same sign of weight. So this is the analog of the Hilbert-Manford criterion in GIT. But so general test configuration or deformation is a very has many possibilities. It might have complicated structure, but so if possible, we want to consider more simpler one. So this is studied by Ross and Thomas, which is called deformation to the normal cone of subscheme. So let XL be a polarized manifold, and we take a subscheme of X, and we consider necessary constants of Z respect to the polarization of X. Then first, we blow up X times C along the Z times 0. So and the second, we take relative ample line bundle LC, which is defined by L minus CP. P is an exceptional divisor of first blow up. So if C is contained in the interval from 0 until necessary constant, and C is rational, then calligraphic LC is ample. And we have a natural C star action on calligraphic L and LC. characteristic X and LC. So Ross and Thomas proved that these three things construct a test configuration or deformation of simple deformation of polarized manifold XL. So the following is helpful to understand what is deformation to the normal cone. We blow up this central fiber, then we have a deformation of XL, because this is a general fiber which is isomorphic to the original manifold, but the central fiber is a blow up of X hat is a blow up of X along the G, and the central fiber is X hat cap union of the X hat and the exceptional divisor. So then we can ask the multiple ideal subscheme B phi infinity or Collat's divisor violates K stability, like by using this simple deformation. So the answer is Collat's divisor cannot destabilize. It is a very easy calculation, because from easy calculation we can find if any divisor is numerically equivalent to the anticanonical divisor, then such divisor cannot destabilize by in the Ross-Thomas sense. So how about phi infinity? In general, the answer is no, but we have a possibility to overcome such difficulty. So let me explain by examples. So first example is a blow up of CP2 at one point. This is not K-Einstein manifold, and this is Fano manifold. So in this case, d phi infinity is 2 times exceptional divisor. In this case, if we blow up along the d phi infinity times c times 0, then this deformation to normal cone destabilize the manifold. So first case, the answer to the question is yes. But the second case, the answer is no, because in this case, d phi infinity is numerically equivalent to anticanonical divisor. This means d phi infinity cannot destabilize the manifold. In particular, 2007, Dmitry Panov and Julius Ross proved any subscheme cannot destabilize such manifolds. It means if we know the precise multiple ideal subscheme, it cannot destabilize. So we need another thing to overcome this difficulty. But the difference of these two cases is first one, here we consider the multiple ideal subscheme of gamma d phi. If we vary gamma, then of course this ideal shift will vary along gamma. But first case does not jump along the gamma, because just one component. It has just one component. But the second one, d phi infinity has 2 types component and 2 different coefficients. So this means multiple ideal subscheme of gamma phi infinity jumped at some point. For example, if we take a gamma equal to 1, then its multiple ideal subscheme is this one. But if we take gamma equal to 1/3, then its associated multiplier ideal subscheme equal to E naught. Sorry. The blow up of CP2 at 2 points, we have 3 curves with -1 self-intersection. So E1 and E2 comes from the blow up, comes from the exceptional divisor of blow up of CP2 at 2 points. But the central -1 curve comes from the blow up of CP1 times CP1 at 1 point. Then we can calculate this. We can have this observation. So this means it says we could blow up not single time, but twice along this one and this one. So actually, if we blow up of x times c twice, then we can have a destabilizing test configuration. Second, this one. So this is one of the possibilities to overcome the counterexample of Fano and loss. So then I'd like to stop this with this final discussion. So we have some idea to construct a destabilizing test configuration from multiplier ideal subscheme. The remaining problem is what is a d phi infinity precisely? So in other words, how can we make d phi infinity restrictive without rich flow? It means in pure algebraic geometry. So I hope we can make use of alpha invariant or log canonical threshold in algebraic geometry version. So maybe this quantity will be discussed today, next lecture or tomorrow. But initially, Tian defined alpha invariant by a purely subharmonic function. But that quantity can be defined also a log canonical threshold like this. So I hope we could determine d phi infinity by using this quantity. For example, we could ask following question. So in this question, I assume that X is toric Fano manifold. So then the question is there any torus invariant divisor which is linearly equivalent to minus m kx and md phi infinity is contained in the D scheme theoretically, and this D attains alpha invariant. But in general, this equality is a very delicate problem. But I hope in the toric case we could take a divisor satisfying this equality. And log canonical threshold of both divisors is equal to the same one. So the question is, can we find satisfying these conditions? So actually, in toric case, we have a combinatorial formula to calculate alpha invariant by Janson. So let me confirm the previous two cases. So first one case, d phi infinity is a 2 times exponential divisor. So in this case, we take for 4 times E and plus 3 times F plus 1, F plus 3. F plus 1, F plus 3 is two zero curves in the first, two zero curves in the blow up of CP2 at one point. This means we have 4 curves in the surface. So 1 minus 1 curve, which is the exponent divisor, and 2 zero curves, and 1 plus 1 curves. So in this case, alpha invariant is 1 over 2, and this is the same as log canonical sets for 1 over 2 times d. The second case, as I said, d phi infinity is just an anticanonical divisor. So we can take d as the same one. So in this case, alpha invariant is 1 over 3. It is equal to the log canonical set for of xd. So the previous question is, previous conjecture has held at least the surface case, the toric Fano surface. And I already observed most, I have already observed in the toric Fano threefold case, the previous conjecture also holds. So I hope the as a generic case, in other generic case, this problem, this conjecture is true. But I don't know. I'm not sure. So if we can find precisely d phi infinity, so then we could construct this stabilizing test configuration by blow up. So I hope finally, eventually, I hope these schemes would give a concrete criterion to determine the case stability of Fano manifold by using birational geometry. So I want to stop here.